Hello everyone. So this video is going to walk us through the distinction between local maximum and minimum points and global maximum and minimum points. Let us get started. Okay. So far we've been talking about critical points and the first and second derivative tests and trying to understand where whether a particular point is a maximum or a minimum or a point of inflection. And what I would like to draw your attention to is the fact that when we started off by analyzing a figure that looks like this, and we told that P is, we wanted to check whether P is a maximum point or not. We were told that P here actually attains its maximum value in the neighborhood of this point. And remember the first derivative test, we were looking at what happens immediately to the left of P and immediately to the right of P. And we're trying to understand the behavior of the function in the vicinity of that point. And similarly, when we were talking about minimum points as well, we were trying to understand what is happening to the function around the particular critical point. Is the function falling just before Q? Is the function rising just after Q? And so on. So essentially what we were doing is we were interested in the behavior of the function in the neighborhood around that point. Now, if at a particular point, the function has its maximum value around that point, if the function has its greatest value in the neighborhood around that point, then we call that particular point the local or relative maximum. So local or relative maximum. Similarly, if at a particular minimum point, if the function has its lowest value in the neighborhood around that point, which happens to be the case here, right, Q, then this particular point Q is called the local or relative minimum. So what does this term local here or local or relative here signify? We are identifying points where in the neighborhood of that point, the particular function is either peaking or it is hitting its lowest point. So that's where the local word comes in. Now, oftentimes in economics, when you're dealing with optimization problems, a function may actually have more than one maximum and more than one minimum point. What do I mean by this? So you may have a function that, say, for instance, looks something like maybe this. And if I just if I put this on an x or y axis, I know that this is a critical point. We have another critical point here, one more there, another here, and so on. And based on just looking at the graph visually, I know that this is going to be a max, and this is going to be a min, another max here, and another min here. And all of these points, right? These are all local maximum and minimum points, because if you notice, in this neighborhood, the function has its maximum value at that particular point. In this particular neighborhood, the function has its minimum value at the critical point. In this neighborhood, we have a maximum. In this neighborhood, we have a minimum. But notice how in one particular function, we've already seen two maximum points and two minimum points. So how do we go about working in such cases? So that's one thing. Another thing is that sometimes you may have functions which, okay, so there's another point to keep in mind. So when I tell you that we're dealing with a maximum or a minimum point, what it effectively means is that the function is either having its maximum value at that point or its minimum value at that point. And so far in the graphs that we've been seeing, we've been having peaks and troughs. So we've been hitting a peak or we've been hitting a bottom and so on. But sometimes you may have functions which don't necessarily have to hit a peak and return. Rather, you can have functions that either continue to increase indefinitely or decrease indefinitely. So do such functions actually have a maximum or a minimum, have a single max or min if they continue to increase? or in other words, is the function actually having, can you put a number and say, okay, this is going to be the maximum value of the function, or this is going to be the minimum value of the function. So that is still a lot of words that I just said. So sometimes the behavior of the function for really large values of x, meaning if we stretch the function, if we look at the function over its entire domain, either plus infinity, if it's, if x goes to plus infinity or minus infinity in two ends of the x-axis, the behavior of the function may be such that the highest maximum values that we find through calculus or the lowest minimum values that we find through calculus are all going to be needed. And what is this going to look like? So suppose I have a function that maybe looks like, let's say, looks like that. And this function is actually, if you go further left from this point, the function is just going to continue to decrease, or rather it's going to continue to have negative y values. If you head in this direction, the function is going to say, keep increasing. Now, I know that this is a local maximum, and I have a local minimum here, and another local maximum, and another local minimum. But notice how, if I'm interested in actually finding the maximal value of the function, that is going to come somewhere in that range, right? In this part of the curve. And you can never pin down and say there is a single maximum value. And similarly, you can never pin down and say there's going to be a single minimum value for this function, because it's just going to keep going on. So this brings us to the concepts of what we call absolute or global maxima and global minimum. So a global or absolute maximum is the point where the function obtains its greatest possible value, which is what I've just been describing. So if you have a local maximum point, say x star, y star, with the additional property that the y star so obtained at that local maximum point is actually the largest value for that function for all x that belong to the real number line or to the domain of the particular function, then that particular y star, that is, if y star is the greatest value of f of x, then that point is actually called the global maximum. And sometimes there may be more than one x value, which will give you the global maximum point. And that x may or may not necessarily occur at a critical point. And once you see a few graphs, this becomes easier to understand. But for now, all I want you to take away is that a global or absolute maximum is the particular point in the function where the function achieves its greatest possible value. Now, how do you find this global maximum point? Well, step one is we know how to find the local maximum points, right? Using the critical values in the first and second derivative tests. Now, start by finding all the local maximum points, which is essentially get your list of critical points and figure out which ones are maximum and which ones are minimum. Once you have that list, if there is a global maximum for that function, compare the maximum values that you obtain from all the local max points. Whichever one has the highest value is a candidate for the global maximum. Is it enough if we just do that and can we stop there by just comparing the local maximum points? No, because as I told you earlier, if you're going to have a function that is something like this, then you have to evaluate what's actually happening to the function for large values of x, either positive or in the negative direction. Therefore, so the either step is, if the only true way to find if a global maximum exists is to sketch the curve and understand how y behaves as x goes to plus and minus infinity. So that's the sequential way to figure out if a global maximum exists and what it is in the case. Let's see a couple of examples to try and understand what's going on. So let's focus on this first function. Y is equal to 2x cubed minus 3x squared minus 12x plus 9. And we've been working with this function for a few lectures now. And we have two critical points, one which is at minus 1, 16, and another one which is at 2, minus 11. Now we have a local maximum at minus 1, 16. Does this function have a global maximum? Maybe this graph is insufficient to understand that, so let's check it out. So let's actually plot. Let's go to Desmos and let's plot and see what's happening. Right. So this is the particular function we're looking at. And so the red line that you see is a graph of this function. And so what's happening? So we have these two critical points here. So that's minus 1, 16 there. And I have 2, minus 11. Now what's the general behavior of this function as x goes to plus infinity? Well, it just seems to keep increasing. And what's the general behavior of the function as x goes to minus infinity? Well, the function just takes on negative values. So can we say that minus 1, 16 is the global maximum here? No, because the function is going to have higher y values to the right as x goes to infinity. And it's just going to keep rising on forever. So there is actually no global maximum. So let me come back to my notes. So no global maximum. Let's look at another example. So I have here a parabola which has a local maximum at the point 1, 4. So 1, 4 is the local maximum. Is it also the global maximum? Let's see. So let me go back to my response. We'll uncheck that and maybe look at the second function. Okay, so this happens to be a downward open parabola. The parabola is at most going to just have one maximum point, a downward open parabola. And where does that happen? It happens at 1, 4. So, and we know that for positive and negative values of x, the function is just not going to have any more maximum points. So the maximum value of the function is obtained at 1, 4. Therefore, 1, 4 is also the global maximum. Is also global. Now, I have another function here. So we have a maximum at P and Q and R. So we have 3 local maximum points. Now, I actually don't know the functional value of this particular function. I don't have the expression or the equation for this. But from the graph, I can kind of sense that the function is just going to keep, this will probably be how the function looks to the left of the point P. And to the right of the point R, the function looks like it's just going to continue onwards. So we have 3 maximum points. And it doesn't look like the function is having a peak anywhere else. So we have P, Q, and R are the local max points. And we notice that at P and at Q, the value of the function is actually greater than it is at the point R. Therefore, P and Q here are global maximum points. But then again, the best way to verify this is to sketch the curve fully, but we don't have access to that information. So at least based on what we see here, you can say that P and Q are the global maximum here. Another way to think about this is if you are evaluating local and global maxima and minima in this particular range of the function, in this particular interval, then we clearly know P and Q are the global maximum. So that's the distinction between local and global maximum points. So I will stop this video here and I'll see you in another brief video where we go over the idea of global. So I shall see you in the next video.